Hello guys, welcome back. So in this video today we're going to be continuing with our previous problem on the derivation of stress resultant, particularly the hoop stress resultant and meridional stress resultant. So if you remember in the previous video, of which I will advise you to watch it if you haven't, because this video is a continuation of um, that part video. So in this video, so basically we're going to make use of finite element analysis to actually try to compare the results of the hoop stress, particularly because if you remember in our previous question, I'm gonna slide to it now. We were asked to find the thickness that the shell should have in order to be able to take the maximum stress of 50 megapascals. This was number 2 here. If we take gamma as the unit weight of water as 10 kilonewtons per cubic meter, and given that A is equals to 10 meters, H is equals to 20 meters, estimate the minimum constant shell thickness T that will ensure that the maximum compressive stress induced in the shell by the external hydrostatic pressure does not exceed 50 megapascals. So we did work out this question. If you remember, we went through all this theory, and we went into deriving the stress, the meridional stress expression, and then from from determining the meridional, we went to finding the hoop stress, and we did find that the thickness that the shell should have was 10 millimeters. So what we're going to do now is we're going to model this problem using finite element analysis. Particularly, I'm going to use abacus. So this shell, we're going to model it having the thickness of 10 millimeters and try to see if we model it having the thickness of 10 millimeters, are we going to find that stress, or the maximum stress of 50 megapascals as indicated here in the question? Are we going to find it? Are we going to get to derive that, or basically we are trying to compare to see whether we are indeed getting that 50 megapascals using finite element analysis. Okay, so it's nice because when you're in the industry, of course I do not have that much experience, but I'm sure other people could relate who do have that. You would not go through all this trouble of having to derive those stress resultant manually. You would definitely be wasting time. So you are always advised to use these software packages, FEA packages, to deal with this problem. Okay, so that's what we're going to do now and see if we get the same thing. Okay, so now let's start without further ado. So basically we're going to start first with getting our drawing our part. We're going to draw the part. Okay, let's call it spherical dome, and just make it yes, let's make it spherical dome. And of course, remember our spherical dome was loaded axisymmetrically, and also the spherical dome itself, the structure, it has symmetry. It has symmetry about that one axis, also about the y-axis, the x-axis. It has symmetry. So we're going to rather try and use axisymmetric, and the reason why we do that is basically we're trying to save computational time, because when you're dealing with structures that are symmetric, you should know this, of course. You remember when we did frames in undergrad, when we analyzed frames, if the frames seem to be symmetric and the loading also applied is symmetric, you would rather use sophisticated methods of you having to calculate the reactions, forces, and so forth, And one of the renowned method of using the analysis of symmetrical structures with symmetrical load, it's group theory. Group theory is one of the most effective methods of analyzing such structures. So you're basically saving time, because when you're making a structure the whole as it is, or a spherical dome as whole as it is, Abacus or the finite element software, it's going to repeat the same calculations. Which wastes a lot of time. And also, even when you do mesh convergence, which is what we're going to do now, when you do mesh convergence, it's gonna sometimes crash because you're making your mesh or your element sizes finer and finer and getting more nodes, and sometimes your software could crash. So rather, when you're dealing with such structures that are symmetric, you use this particular technique. Okay, so it's a deformable structure, and of course it's a shell. We're dealing with a shell. And approximate size grid, we're going to use 200. It's fine. Okay, so now we're going to try and draw. Okay, so let's first do that. That's 0 and that's 10. So remember our radius A it's 10 basically. So that's what I'm doing now, and the thickness of our structure, it's 10 millimeters. So that's going to be 10.01, 0, because I'm using meters, not millimeters. I'm using meters. So 10 millimeters, it's 0.01 meters. So that's 10.01, 0, and it's 0, 10, and it's 0.10.01. Okay, so now we okay. Okay, so we repeat the same thing. Okay, so now we join it because it needs to be a closed section if we're dealing with axisymmetric, shelled, deformable. Okay, all right, and then it's done. Okay, so of course this is how we're going to do it. Of course it's symmetrical about this axis, the one in dotted yellow. And of course you would expect it to be this thin, because remember this thing, it's 10 meters in radius, and therefore it's 10 millimeters thick. So you're gonna expect to see it very, very thin, as you can see. Okay, so now let's assign our material properties. So if you remember in the previous video, I did say we should make it concrete, but as I was reading the question, I was like, you know what, let's just rather stick to it. Let's make it metal. So we use steel materials. Okay, we use steel materials. So it's an elastic analysis. So we did ignore the self-weight in that previous question, so we're not going to include the self-weight as well. So it's elastic, elasticity, elastic. So the Young's modulus of steel, it's 200 GPa. So since we're using meters, it's going to be 200 E9. 200 E9, and then the Poisson's ratio, let's use 0.3 for steel, and it's okay. All right, and then from there we create a section. Let's make it a solid homogeneous. It's a plane stress or stress thickness. It's going to be 0.01. That's the thickness of our structure, which is 10 millimeters. Remember, I'm using meters in this instant. So it's going to be 0.01, and that's okay. Then I assign the thickness to the structure, and then the thickness, the assignment, or when you're assigning the thickness, you can use sometimes from the geometry. So that means it's from the geometry part itself, or you can use from the section that you just evaluated just now, the one that I just did just now. So I'm going to use from the section, so it's okay. And just want to see if it's colored. If it's colored, then it means it's fine. And then from there, I create an assembly. I assemble. So this is the assembly is what the model, not the model, is what Abacus models, okay, in this assembly, okay. So it's one of the most important stages. So whatever that you assemble in here, it's what you're going to model, okay. And from there we go to step. So it's a static, general static analysis. We are not doing any buckling, although I could say in reality 10 millimeters it's quite thin, so one could expect buckling failure to be susceptible in this case. So you could do the buckling analysis to check as well and solve for the eigenvalue solutions, but it's fine for now. We'll do static general. And of course, we're not doing any nonlinear geometric. So this is now when you count for nonlinear effects or basically large displacements. So we're not going to do it. We're just doing the linear elastic analysis. So it's just going to be that off, and then the time period obviously will be 1. You don't have to describe, but okay, we could describe, say, spherical dome analysis. Okay, and then no heating effects. Let me see. Okay. All right, from there now we can go to assigning our load. First, let's put our boundary conditions. So boundary conditions is extremely important in this case as well. In fact, my lecture did say it, that if there's one thing that you should be careful with using finite element analysis, your results or your solution is heavily affected by two things. It's your boundary conditions and your mesh. Those two, if you get them wrong, then it's over. It's over. So you can't get your boundary conditions or your mesh, because your mesh, that's where now you put your elements, and your elements have nodes to it, and your nodes, that's where your forces is being transmitted through, and that's where now if your elements, some of your elements are terrible, so you're gonna get results, or basically even when you do mesh convergence, then it's going to diverge as well, and then you're not getting any solution. So let's do our boundary conditions. So our boundary conditions, we're first going to start with that part. So it's continue. So we're going to take this part here because it's symmetrical about the x-axis here. So that's done. Okay. So that means the x sim here, it means it's symmetrical about the x-axis. So that means it's just that I can't show it through the computer, but that means this thing it's running a loop around the x-axis, so it's symmetrical about the x-axis. So I would do that, and then I'll say okay, and then from there we create another one, and then it's also here, it's now symmetrical about the y-axis. So that means it goes around the y-axis here. Okay, means it loops around the y-axis like that, if you can see clearly with my cursor. So it's y sim, so that's okay. All right, so now let's assign our pressure. Remember our loading now, it's of course pressure, hydrostatic pressure to be precise. So let's continue, and then we apply our load on the edge, because that's where the water is in contact with your shell element. Okay, that's okay, and then it's hydrostatic pressure, and then from there, remember our let's go back. So h here it's 20 meters, sorry, and our unit weight of water, it's 10 kilonewtons per meter. So since now we're using newtons per meter squared because it's pressure, So it's going to be 10,000 newtons per cubic meter multiplied by 20 meters. So that's going to be 200,000 newtons per square meter. So that's 200, 1, 2, 3,000. Okay, and the zero pressure height, it's going to be at 20 because that's the surface of the water. And then the reference pressure height, that's where now the pressure is at its max. So it's going to be at 0. Okay, and we said okay. And then let's check, and then this is what we should expect. And if you remember when we were dealing with our analysis here, we did say that for hydrostatic pressure, our P phi, which is the loading component that is tangential to your shell element, it's going to be 0 because pressure acts normal to the surface. This is exactly what I meant. Pressure acts normal to the surface. Okay. All right, so now we're done with the loading, and then we can go to the mesh. So this is extremely important as well. Okay, so we're going to mesh our part. So we do that, and then it's done. Okay, so obviously we're gonna use a quadratic shell element. A quadratic shell element, it means it has 8 nodes, of course. If it's a linear, of course, that is if you're using square elements, it has 8 nodes. If you're using triangular elements, that means it has 6 nodes for quadratic. Whereas for linear, it will have 3 nodes if it's triangular, and then 4 nodes if it's a square element. So we're going to use a square element. So the more number of nodes you have, the more accurate your precision gets to be, or your analysis gets to run quickly in terms of getting to the quicker answer. It gets to the solution quickly. That's what I meant. Not quicker answer. What's that? I meant quicker time. It gets to the solution at a quicker time. Yeah. Okay, so it's quadratic. Of course, that's what we're saying. And then we're using reduced integration. Reduced integration, that means basically your element has one. If it's a square element, of course, that means it will have one Gaussian coordinate. So it's somehow you're reducing the time it takes for it to run to the solution as well. So it's all about that time effect, because believe me, when you're running these problems or solving these problems, when it's a huge problem that you're dealing with, the computational time could take a while, and you get to find out it even crashes. So sometimes you don't even have to do what mesh conventions, and that's when you have to resizing your element size, and imagine now you're gonna have to wait. So it does take time. So reduced integration, it just means that your element has one Gauss coordinate. It has to do with the Gauss curvature. If you all remember the integration, when we deal with integration, we were introduced to Simpson rule. It's one of the methods to approximate your area of the element, and then we have also what we call the Gaussian curvature. So it comes from that. Okay, all right. So it's reduced integration is that, so that's okay. So now we're going to size our element. So I'm going to start here. And then here as well. Okay, so I'm going to pick my elements by numbers. So I'm going to make 3 elements because it's very thin. It's going to be 3 elements, and I say apply, and then okay. All right. So now my global size elements, I'll use 1. Let's first start with 1 because we want to run mesh conventions. So let's first start with 1 and see how our solution gets to be. So let's apply, and then okay. And then of course we want to use quad square elements, as I said, and it's going to be structured. We want them nice and structured. Okay, and then from there we run the mesh, and that is okay. It doesn't look nice when you see it in this manner, but it's just that it's quite one global size element. It's big with relation to the size of the structure. Okay, so now let's run the job. Okay, let's create. It's model 3. Then okay, and then let's submit. Okay, so it's done now. All right, so you see the time it took to analyze this structure. If structure you did not use axisymmetric technique, it was going to take probably twice as long it would take to complete that. Yes, of course, I mean 3 seconds compared to 6 seconds, it's unnoticeable, but sometimes when you're dealing with bigger structures that you'll be analyzing, 30 minutes could turn into an hour, or 2 hours could turn to 4 hours, which is the time that you would not have as an engineer in practice. So let's go to the results. Okay, so let me just change that because I did make my settings here. Let's do apply. All right, okay, so now let's go to what is it, my settings. Let me just change the settings here because I'm just looking at something. In fact, let me leave this maximum and minimum because I did apply my settings here with Abacus to show you where the maximum stress is, the minimum stress is. Okay, and let us also be aware that the stress in terms of the units here, it's in terms of pascals because we used meters, so Abacus uses newtons and meters, so it's going to be newtons per meter squared because it's stress, which is what, pascals. Okay, so pascals in terms of megapascals, because you want megapascals, it's going to be to the -6. So basically here what you're seeing, it's 4.6 megapascals, but remember we are looking for what? We are looking for 50 megapascals, if you remember in our problem. Okay, but now what is the stress that we're looking at? So first let's start with this is the von Mises stress. Okay, so and then this is your S11 sigma x S11, and then this is S22, this is sigma y, and then that's S12, this is tau xy, this is your shear stress, and then sigma 11 and S22, I mean sigma S11 and S22, those are your normal stresses, which is sigma x and sigma y. Okay, but this is not what we are looking for. What we are looking for basically here is the hoop stresses. So that means we need to change the orientation of our coordinate system in terms of using rectangular coordinates to spherical coordinates. Okay, so we're going to do that. We create a coordinate system. So now we're not using rectangular, we're going to use spherical. So if you remember now when I said if you did vector calculus, this will really ring a bell, that why were you using these spherical coordinates, rectangular coordinates, or cylindrical coordinates? If you remember, rectangular coordinates, it's x, y, z, and then spherical coordinates, that's where you have your rho, your theta, and your phi. And your cylindrical is r, and then it's theta, and then it's z, if I remember quite well. So now we're using spherical coordinates because we're using a spherical dome. So that's a fixed system, it's continue, and then okay, so now we're going to apply those spherical coordinates. So let's go to options. So we transform our coordinates to our user specified, which is spherical. Let's run apply. So now as you see, they change. Okay, but what we're looking for is the hoop stress. Hoop stress, it's S22 with Abacus. So this is what you have. This is what you have. As we can see here, your stress, in fact the maximum stress, it's what, it's 1.87, and then it says here the minimum stress is 6.46, which is not what we're looking for. Okay, which is not what we are looking for. So let's remesh. Okay, so now let's remesh our shell element. Okay, so now instead of using 1, I'm going to use a 0.5. 5. So let's say apply, and then we run, and then it's done, and then we rerun the job again. So this is now me converging. I'm doing mesh convergence now, because I'm decreasing the size of the element, and then get to see if my answer gets to converge to what I want. Okay. That's what I'm basically doing. And of course, the more number of elements, because when you converge, when you make your element sizes small, that means you are increasing the computational time, or the time it takes for you to reach to the solution. Let's go to the results, and then we go to S22, and then from there we do the same thing. Remember, it gave us this in terms of rectangular coordinates. We do the same thing. We go to spherical coordinates. So that's continue, and then we apply that transformation, and it's okay. All right, so let's see what we have. So now the maximum is 2. So this negative 2.086 times 10 to the 7, if you convert it to megapascals, because this is in what? It's in pascals, so it's going to be 20.86. It's going to be 20.86. It's negative because it's in compression, which is what we'll expect. So it's 20.86. 20.86. Okay. In fact, let's start doing our convergence here. So that's 0. I just want to put it in. So it's negative 2.086, and then it's E7. Oops, sorry. Just say 2.06 times 10 to the 7. So it's going to be, actually let me write it in this manner. So it's going to be 2086 and 0.00000. 2.09. Of course it's negative. Okay, that's what we have for now. In fact, this is for element size 0.5. Oops, sorry. And then this, let's just leave it for now, because I didn't take it down. So we can just, in fact, we can make it, we can rerun. I'll go back and redo the mesh. Then let's submit the job. So I'm just redoing the size, the element size 1, so that we can get the result and record it into Excel. Okay. So this is what result. So I'm gonna go to spherical again. Okay, so the maximum that we have here, it's 1.87 times 10 to the 6, so it's 1.87. So let me just do it. It's 1874. So that's 1874, and then it's, I think it's positive. Yeah, it's positive. Oopsie. This is positive, so that means it's in tension. Okay, all right. So that's what we got. So now let's remesh again. So let's decrease the size even further. So we went from 1 to 0.5, and now from 0.5 we go to 0.1. Let's do that, and then we mesh. Okay, so if I could zoom, you can see now the element size, it's getting smaller and smaller. Okay, the element size, it's getting smaller and smaller, and as we get smaller we should get to the solution. Okay, so let's submit again, run the job. So now this is mesh convergence. You see how much time I'm taking, and this is for a simple element structure. Now imagine the real world problems, the time now you will have to take if you do not maximize in terms of your computational time. You will never finish in time. So yeah, because remember, if you're even in the industry, sometimes you don't even know the solution that I have, is it the right solution or not? Hence why you have to do mesh convergence always to see if your solution is converging or not. Okay, so now let's go again. S22, that's the hoop stress. I can repeat, it's the hoop stress, and then I change my coordinate system again, and then results, I convert them to transformation. Okay, so now we're getting closer. So it's what? It's minus 4.87. So times 10 to the 7. So now that's 48.7 megapascals. Remember, ours it's 50. So it's 48.7. 48.7. Let me just do this. Okay, so this is 0.1. We got, let me just go into it. It's 48.7487. Okay, so it's 487. All right. Okay, so of course here the convergence is in terms of percentages. It has to do with the jump in terms of your result. So that means your result from there to here, from element size 1 to element size 0.5, the change in result, it's 109%, and then from element 0.5 to element 0.1, and of course 0.5, 0.1, these are your element sizes. Now the change, it's 57% in terms of your solution. So you can see how effective this mesh convergence gets to have. So until we have a change of result less than 5%, then we haven't reached our solution. But if the change is less than 5% in terms of your solution, from your previous solution to your next solution, or your previous element size to the next element size, if it's less than 5%, then it's set to be accepted that should be your solution. Okay, so now let's further decrease our element size. So let's go to the mesh, and then we go to, now from 0.1 we go to what? 0.05. Okay, and also the nice thing about axisymmetric, it's that it allows you to decrease your element sizes as small as you can, because your structure itself, it's not that big. Therefore, it allows you to have as many nodes as you want, especially if you have a license that is limited in terms of the node numbers. The one that I have is limited to 20,000 nodes. So that's the great thing about axisymmetry. Okay, so now that's yes. Okay, if I zoom in, you can see now this element size, it's getting smaller and smaller, or your elements getting smaller and smaller. So let's resubmit the job. Okay, so let's check the results now. Okay, so we're doing the same thing over and over again. So I don't want to have to repeat it now. You guys should have taken the leap of it of what I'm doing. Okay, so now it's minus 4.977. Now this has converged. I think it has converged. So that's your maximum stress. It's minus 4.977. Okay, so okay, so we can see now this is what 2.15%. So this should be acceptable. You know that if you round it up, it's 5, but let's further decrease our element size to see. That's mesh. Let's further decrease it to what now? 0.01, apply. And okay, resubmit the job. Okay, all right, let's check. It's the same thing again. Oops, S22, and we're using spherical. That's options, and that's transformation. Use component. That's apply. Okay, so as you can see now, it's here. It's now minus 4.992. Okay, so $4.992. Okay, all right. So yeah, that's your curve, how it looks like. As you can see, it has converged, because if you look here, we have reached our solution there, which is what, -5 pascals. I mean -5 times 10 to the 7 pascals, which is equivalent to 50 megapascals, or -50 megapascals. And it's negative because it's in compression, as we should have expected. And yeah, and that's it. Of course, I can try and make this view and make you see, because remember I did remove it. Let's just make it, let's apply, and that's your view, of course, of your cylindrical dome. Let's just remove it, and that's how it looks. Okay, so as we expected, we should get our solution. So this is now the power of finite element analysis. This has taken me, I'm not sure how long it has taken me now recording this video, but it's not a lot of time. But then you should know that that's your solution, because it has converged. It's not going to be changing. Of course, you could decrease your element size smaller and smaller. You would probably even get to -5 times 10 to the 7 pascals. And yeah, that's it for this video, guys. And yeah, hope you enjoyed it. Take care. Bye bye.